Now let's look at a second technique for using data analysis of experimental results, and that technique is called regression. When do we use regression? Regression is particularly useful under two conditions. First, there are a large number of variables that we believe might cause the effect, and second, when these variables don't come in neat categories, but they might instead be what we call continuous variables. When we looked at ANOVA, we gave the example of trying to study the effect of pennies a day framing on spending. And we said that people could either be in a condition where the expense is framed as pennies a day, or if it is expressed as an aggregate fashion. That was the only one variable that explained spending. But it could be the case that we are looking at several variables that we use to predict spending. That's when regression might be more useful. Also, in the pennies a day case, the variable was categorical. In other words, you were either in the pennies a day condition or you were in the aggregate condition. It was one of two. Now let's look at a different experiment. Let's imagine we are trying to study the effect of your credit limit, the credit limit on your credit card, on your willingness to make a purchase. The credit limit is not a categorical variable. It is what we call a continuous variable. You could have all kinds of credit limits. It could be $5,000, $1,000, $3,600. Absolutely any numerical dollar value could be your credit limit. And that's where regression is particularly useful. Now let's imagine we are doing an experiment. We collect data from several people on their credit limit. We're going to call that X. And we also measure from those same people a variable Y. Let's imagine that is their willingness to make a purchase. And we've got data from each of these people on those two dimensions. So for example, for this individual, we know that this is their credit limit and this is their willingness to make a purchase. What does regression do when we have data from several such people? What it tries to do is it tries to find a line that best expresses the relationship between X and Y. And that line might look something like this. So what is this line? Let's imagine we've got this dotted line. This dotted line, as I said, might express the relationship between X and Y. But if you look at any given individual here, their actual data deviates from the line. And let's call this deviation an error. Okay, so for each one of them, there is an error. We can take all these errors, we can square them, and we can add them up. And the best line is the one where the sum of these squares is the minimum. So what is regression actually doing? Regression is selecting a line such that the sum of the squares of these errors is minimized. That is what we call OLS, the ordinary least squares approach to regression. Now once we have a line like this, we can actually make predictions about Y based on X. Right? So we say, well, what happens if X is a certain value and that value is there? We can throw up a line and we can make a prediction about what the Y is going to be. And this regression line is written out in the form of a simple equation, which we'll talk about in a minute. But let's imagine the following. What happens when X is 0? What happens at this point? We're going to say, well, there's still some very basic purchase intention. And that basic purchase intention is something that we're going to call the coefficient or the intercept. So A, right? A on this picture is the intercept. It is the value of Y when X equals to 0. And B is the slope of the line. And together, our regression line can be captured by this equation, Y equals to A plus BX. So that's what a regression line looks like. If in fact we had a lot of x's, a lot of variables that we believe explain y, then our regression line looks a little bit more complicated, but this is the simplest form of the regression line. Again, how do we interpret this? When x equals to 0, when the credit limit is 0, there is still some basic willingness to purchase. That's going to be A. B is the slope, which talks about the effect of credit limit on willingness to purchase. The bigger the slope, so for example, if my slope was very sharp, then it says that if I increase x by small amounts, we get pretty large increases in y. If the slope is flat or very gentle, then the effect of x on y is low. Now, as we said, if there are a large number of x's, then our regression line is going to look something like this. It's going to look like this, where y is a plus b1 times x1 plus b2 times x2, where x1, x2 are the various different variables that explain. And then finally, in this example that we looked at, y is a continuous variable. We simply ask people, what is the likelihood that you would make a purchase? But let's imagine that the variable is categorical. Let's say we change the credit limit, and we simply ask people, will you buy a certain product or will you not buy it? Or in general, it could be multiple levels. If we ask people to choose option A, option B, option C, the intuition behind the regression is still going to be the same, but the kind of analysis that we're going to use is going to be called a variation of this. It's called a logit, L-O-G-I-T, regression. We use a logit regression when our x's are still continuous, but our y, which is a dependent variable, is a categorical variable. So in sum, regression is a very handy tool when you have complex, continuous data, lots of variables that all explain one particular y. Regression is a fantastic tool to use. And in the next few units, we will actually see a lot of examples of experiments that have used both the regression approach as well as the ANOVA approach in reaching their conclusions.